Thank you, Chairman, and I would like to thank the organizers of this very interesting workshop to invite me here today. So this talk is an approximation of PDEs, but with parametric PDEs of PDEs with random parameters. So the approximation is mostly with respect to the parameters. I will not discuss the approximation with respect to the physical space or the time. And let me acknowledge the co-authors. These collaborators to this work are Raul Tempone, Giovanni Migliorati, Albert sitting here, and Abdella Shkifa, who have contributed different parts of this. So the focus might be slightly different than what you have heard in these days, but the technique that I propose here has actually a lot of similarities with what the compressive sensing ideas and what has been discussed in these days extensively. So I will, this is the outline. I will just introduce the type of problems we are looking at and the type of approximation that we would like to use that are basically just polynomial approximations, but high-dimensional polynomial approximations. And then the technique I will discuss today that is basically based on constructing polynomial approximations using just random point evaluations. And I will briefly discuss at the end this more theoretical study we have done with Albert and Giovanni Migliorati on how to construct the best approximation in a class of polynomials. So the really the set here is what is commonly called quantification, which is a very broad keyword, and is something that is, I would say, quite relevant in many applications, mostly engineering applications. So suppose you have a certain model, and typical models are differential models, so maybe an ordinary differential equation or a partial differential equation and so on, and which you believe it's a good model for the reality and is described by some basic physical principles, so let's say conservation of mass, energy, momentum, and so on. So in some sense, this operator here is deterministic. You don't really necessarily want to add the stochastic behaviors to the system. However, in this deterministic model, you have several parameters that you do not control perfectly. And then you would like to include some range of variability, or if you have more information, some distribution function, probability distribution function to account for this. It could be a variability in the system, and every time you run an experiment, you get something slightly different, or it could be just a lack of knowledge, so you're not able to characterize well these coefficients, and somehow you want to be conservative in your prediction. So the parameters could be at this level, whatever. I mean, you have a partial differential model that has 5 parameters, and you want to, for each of them, you want to put some uncertainty bounds. Or there are other situations where maybe you want to describe some inhomogeneities on the medium. Could be some spatial inhomogeneity or temporal inhomogeneity in the forcing term. And in this case, you could describe those objects by random fields. These are infinite dimensional objects. So to recast in this framework, one could always take this random field, expand it on a basis, and then describe it in terms of a countable sequence of random variables. Okay, so in this setting, here the dimensionality of this parameter vector, this dimensionality, I call it D, could be very large if you have many parameters, and could even be infinite if you are dealing with these random fields objects. And you can think of many situations where these techniques are of interest and now are being used to some extent. For instance, all what is subsurface modeling. So you would like to model, for instance, the flow of water, oil, gas in a porous medium, and it's clear that you have very little characterization of the properties of the medium. So it's quite common in geostatistics to describe the medium as a random field, even though it's not random. I mean, if you were able to measure in every point, you would have a perfect characterization, but since you can't, you model the uncertainty by randomness, or in seismic applications and so on. All modeling of living tissues, here you have heterogeneities, you have variability between patients, you might have even variations in time, so you might want to add more randomness in this description of these models, or in material science, composite materials, and so you can think of many situations. Of course, there are several approaches to do uncertainty quantification, and probabilistic approach is just one of them. You can think also of some interval analysis or fuzzy analysis or a worst case scenario and so on. But I will focus here on a probabilistic approach because somehow it's nicer in some respect from the mathematical point of view. So if now I introduce a probability measure on this space RD, or the set of possible values of these parameters gamma, then the mathematical problem is nothing but just a transformation of measures. So you have the measure of this random vector here, y, and you pass it through your equation, and somehow you want to characterize the measure of the output. Okay, and of course, if you want to do this, you have to assume that you have a solution map, so in input-output map. So for any y, you get a solution u. So this allows you to propagate the measure. You might want to look at the measure of this, the whole solution. If this is a PDE, this will be a function in some Banach or Hilbert space. So actually, this is a quite complicated task because you want to describe the measure in this infinite dimensional space, or you might want to just look at some specific statistics. So let's say you are interested in the expected value of the solution in every point of the domain, or the variance, or correlation structures, or in many engineering applications, you might just actually look at some specific quantities of interest. So you run a fluid dynamic problem, you're interested in the lift or drag. Those are just two quantities, so those become just two random variables. So at this level here, you're just looking at a function of several parameters, of several random variables. Okay, so this is more or less a setting. This is just a model problem that has been extensively studied in the last years. So this is more related to this porous media flow. So you have a diffusion equation here. U would represent the pressure, the hydraulic head. F is any source or sink of water or other fluids in the medium, and A, the coefficient here, is the permeability. Again, as I said, in many situations you don't really know the permeability, so you want to describe as a random field. So this coefficient should stay positive. So for instance, you could describe as the exponential of some random field, and since Gaussian random fields are nice objects, many people use here a log normal model, so an exponential of a Gaussian random field, and then you expand the Gaussian random field in series, and you will have a parametrization in terms of the sequence of independent Gaussian random variables. For instance, yes, I mean, in principle, you can ask many questions. In this talk, I will ask very limited questions, like if you can approximate the expectation, the variance, or in general, the function in L2 sense, the function or functionals in the L2 sense. So the density here is assumed fixed, known, and that you can sample, so the simplest setting. Of course, there is a big issue on how you come up with a good reconstruction of this density. This becomes more an inverse problem or in a statistical inference, and then you need observations and do inference. So in this talk, I assume this is given, and you can sample it. Okay, so this is one situation, or you could think of other situations like you have a layered material, and in each layer you can play with, you put uncertainties in the coefficients, so you might be in a more finite dimensional case. So you have only a finite number of parameters. Okay, so what type of approximation do we want to do? As I said, I don't discuss in this talk the approximation of the PDE itself. You can pick up any reasonable method, finite element, finite difference, spectral approximation, so on. What I want to discuss is the approximation of U with respect to these parameters Y, whether you want to do this or not. So, and the point is that not for all problems, but for a wide class of problems, this is one example, but there are others, the dependence of the solution U on the parameters is actually very small. Okay? So in this case, for instance, well, under reasonable assumptions on this dependence A of Y, you can show that this dependence is analytic. So you have infinite regularity. You can differentiate this solution map infinitely many times with respect to any Y. Okay, and because of this smoothness, it's not a crazy idea to try to approximate this map U of Y. Even if you are in very high dimension, you can try to approximate this map by, for instance, global polynomials or other spectral type methods. Okay, so it would be crazy if you want to do local piecewise approximation, because if you are in very high dimension, this convergence will be extremely poor. But we can try to exploit this smoothness of the map to do effective approximation. Now, the point is that, so of course we cannot, since we are in very high dimension, possibly we cannot work on just tensorized polynomials, because we will face the curse of dimensionality, so one has to be careful in selecting the proper polynomial subspaces. So I define a polynomial subspace P indexed by lambda, where lambda is an index set, which basically lists all the monomials I want to retain in my approximation. Okay, so I'm approximating in terms of Y. Each monomial will be yn to some power Pn, and P is a multi-index that gives the degree in each variable, and the lambda set lists all the degrees that I'm using each variable. Okay, so lambda becomes my discretization parameter in some sense, and of course the question is what is the good choice for this lambda or a sequence of index sets that allows me to do effective approximation and a converging approximation. So here is a useful concept that actually was somehow proposed, advocated by Hilbert and Rondevaux, on the idea of using only sets that have a certain structure, which we call now downward closed structure, which means that, okay, this is a representation of the set. Suppose you have two variables, y1 and y2, and p1 and p2 are the polynomial degrees, so each red block here corresponds to a monomial. So this one would be the degree 2 and 2, and the structure means that if you have if you pick up a monomial here, all monomials of lower degree should also be in the set. So you don't allow for holes or disconnected parts in this set here. So somehow this structure has a certain rigidity, but it has also certain advantages in working with. Okay, this is also another slide on motivation on polynomial approximation. I'm just recalling a well-known by now result by Albert Cohen, Rondevaux, and Christoph Schwab, and there are many following works that show that if you take, for instance, this diffusion equation and you expand A in an infinite series, in this case for uniform random variables, but there are generalizations also to Gaussian random variables and log-normal model, under the assumptions that you have a uniform boundedness and positivity for this coefficient, for any x and for any y. Then basically you can show that there exists a sequence of polynomial approximations and downward closed sets of increasing cardinality, so lambda m will have cardinality m, for which you can show an approximation, and the rate of approximation here is the cardinality of the set, so the dimension of the polynomial space, to the 1 minus 1 over p, where p is related to the summability of these coefficients here. So basically, what dictates the approximation rate is how fast this series decay. If you have a series that decay very fast, so y here are normalized in minus 1, 1, so for this series to converge, these functions should decay, okay? The faster they decay, the smaller exponent you can take here in this summability of the sequence. Okay, so that's the rough intuition. Okay. Yep.
Is this optimal in some sense?
Good question. Do you have any optimality result by now? There, yeah. Yeah, I mean,
be more subtle and try to understand if they, how they compete with each other growth-wise. But this gets more technical.
But there are no lower bounds proofs of Aron complexity. Yeah, you have, yes, you had one.
So I think what I was really asking was, can you do better with sets that are not downward closed, but are of the same size?
Well, probably yes, but the proof here, this proof here relies on basically stretching arguments, so you really pick up the best term approximation, and you can show and I mean, you don't show better exactly. I mean, when you show this proof, you don't use the downward closeness assumption, but then you realize that to estimate the rate, you see that the sets that you construct are downward closed, basically. So it seems that you don't lose much. You don't lose when you go to this structure here. Okay, so this is a theoretical estimate. So here, really, you estimate the best approximation error. This is not directly computable, so to compute it, I mean, there are many techniques around, but the one I discussed today is just based on random sampling. So, as I said, I suppose that I can sample from the distribution row. So I sample a certain number of points from the distribution, joint distribution row of y. For each one of those, you can go back to your differential problem, solve it, and you get the solution. And then you collect all solutions or the corresponding quantities of interest you're interested in approximating. And you build a polynomial approximation by simple L2 regression. So discrete least squares here, where you try to minimize the misfit for any possible polynomial function in your space. So it's actually a very simple idea. Okay, here I rewrote it for a real valued function. You can do for real valued functions, or you can do for the function itself by minimizing the corresponding norm in the Hilbert space. Of course, if you want to approximate the whole function, you will also have to approximate, take finite dimensional approximations of the Hilbert space. There will be a discretization error of the PDE at this point appearing, but in both cases, actually. Okay, so let me introduce a couple of notations. The P arbitrary polynomial on which I'm minimizing, and this is a function of, okay, now this notation I should have changed it some. So y of omega k, I mean the kth. No, you depends on y is the solution of the problem, of the original problem here. And I have sampled it on a random point, so I got this value uk. And then I minimize overall polynomials that also depend on y.
All right, so V
V,
is sample of the y, yeah.
yes. V is, I mean, in this functional setting, V is a function in the space variable and polynomial in y.
And below you need some Q, I guess.
No, below is the same, but I'm just looking at a real valued function at this point. So I take a functional of the solution u, so let's say the lift, and this becomes just a real valued function of y, and then I approximate with polynomials. Okay. So I introduce a couple of notation. What we are, as I said, answering the previous question, what we actually are looking at is approximation in the L2 sense, L2 with respect to the random variables in the measure. So I will, this will be my reference norm, L2 in the random variables and whatever norm you have in the other variables. And I introduce the corresponding discrete norm, which is just based on the evaluation on the random points. I call it this M norm. I use an orthonormal. I assume that I have an orthonormal basis of the polynomial space that I call psi p, where p is in this index set, so that I can expand the solution on this basis here. Okay, and one last quantity that will appear often later on is this kappa of lambda. This is a quantity that depends on the index set that we have chosen, and can be described in two different ways, two equivalent ways. So it's actually the supremum of the sum of the maximum of those polynomials over all the p in the index set, and it's actually equivalent to the ratio between the maximum ratio on the polynomial space between the L infinity norm of the polynomial versus the L2 norm. Okay. Okay, so of course this minimization problem is just a least square, so when you this leads to a linear system to solve normal equations. So if we expand on the basis of a coefficient, if we expand the solution or the quantity of interest on the basis, we want to find the coefficients, and the coefficients satisfy this equation where D is the design matrix where we evaluate every polynomial in each random point. And I just rewrite it slightly this, so introduce the matrix G, which is 1 over M D transpose D, so it's the Gramian matrix divided, rescaled by M. Okay, and this random matrix here, actually, if you look at the norm of G or the norm of the inverse, those are nothing but the ratio between the discrete norm and the continuous norm. So the norm of G is the maximum over all polynomials of this discrete norm of the continuous norm, and the inverse is the other way around. Okay. So the main tool, again, is contribution from Albert, Cohen, Davenport, and Leviathan. Is a sort of non-uniform RIP, since we are in a compressor sensing audience, that shows that if M is well chosen with a high probability, this G Gramian matrix is close to the identity up to a coefficient delta. So if we define this set and saying that G is close to the identity is equivalent to say that the discrete norm is equivalent up to constants 1 minus delta, 1 plus delta to the continuous norm. And this should hold for any polynomial in the polynomial space. Okay, and where I say it's non-uniform because here I'm assuming that lambda is fixed. So you have chosen a priori the index set where you want to work with, and you just have to show that this holds. And the relation looks like this. That M over log M should be larger than 1 over gamma over this beta delta that scales like this is basically delta square, okay, times this constant kappa of lambda. Okay, and with this you can show that you have high probability of success of having this norm equivalence. Okay. this.
You work to replace empirical model with true norm.
Yeah, but if you have infinite sample, this empirical norm converges to the two norms, so you get close. It gets more and more stable. In the limit m going to infinity, G converges to the identity, so everything works well. So the question is how far from infinity can you be? How many samples you can spare, still keeping this equivalence. Okay. Correct. Yes. You build a polynomial. So yes, I have to say that in the general case, this might be quite challenging. So that you don't know. In this setting here, as I said, I assume the measure. So it's an a priori model. For instance, in this groundwater model, you often model the variability by a Gaussian process or Gaussian field. So in that case, you know the measure, and then it's not difficult. Or in this more, but then if you go through the inverse problem and then you correct the measure maybe by some a posteriori Bayesian update, then of course here it becomes more cumbersome to build the corresponding polynomials. Okay, so here this result is just based on concentration of measure inequalities and the fact that G is a sum of independent matrices and the kappa, this constant here, is nothing but an upper bound on the spectral norm of each one of those matrices. Okay. So basically, I show that the spectral norm of this is a ratio between the discrete norm and the continuous norm, and the discrete norm is bounded by the L infinity norm, so I can use this as an upper bound of each. And once you have this, then you can, again, the resulting expectation was in the original paper by Albert Davenport and Leviathan, so you can show a convergence in expectation, so you can show that whatever you reconstruct with these discrete least squares in expectation is up to a constant equivalent to the best approximation that you can do in the polynomial space, plus a small term. Now, the point is that when you have this result, you have a good control on the set where those two norms are equivalent. So in this set, you can show the equivalence between the approximation and the best, discrete least square error and the best approximation. On the complement of this set, you know that it is small, but the problem is that you don't have any control on the polynomial approximation. The polynomial approximation can become quite wild outside this set. Okay, so for technical reasons, you need to introduce a truncation. So if you know a priori that your function is bounded in some ball, then you build the polynomial approximation, you chop it, and then you can show that this truncated version converges in expectation in this set. You can derive results in probability, similar. This we did in some follow-up works. You don't need the truncation in this case because you just restrict to the set where you have good stability. So you can show that with high probability, let's say greater than 1 minus alpha, alpha is your confidence level, you have that the error that you get from this reconstruction is up to a constant equivalent to the best approximation error, but now you lose a little bit because you have to evaluate the best approximation error in the L infinity norm instead of the L2 norm. So in the well, then you have to particularize. If go back to this result, what was it by Albert? This you can get in L2, and you would get a better rate, 1/2 minus 1 over p, and you can get in L infinity. But this is in the bounded case. If you're in a bounded case, you have to add some weights and. Yeah, you have to come up with this set. So from a practical point of view, in some cases we know the set. We know we have a good idea on how those sets are formed. And if we don't have any idea, I will come back later in the last part of the talk on this. All right, so here are some of the results. So in probability, we can get this type of estimates, losing slightly in the norm, in the best approximation here. One can analyze the case with noise, in case the observations are noisy. Actually, here is a model of noise where you can have certain variability, sigma square. So this is the bounded noise in the mean square sense. And you might have also some bias or some offset. And among the two, I'm in this setting more interested in the first one than the second one. And the reason is that in this case, the idea is that you have your operator, you can sample it, and you can compute the solution. So you will not have random measurements errors in the observation, but you will have discretization errors in the observations. So you don't solve exactly the PDE, you solve it up to whatever discretization you have done of the PDE. So actually here we can include the offset or the bias. In this term here, we can include the discretization error that comes from the approximation of the PDE itself. Okay, so this again is a type of result that one can derive in expectation or in probability. So the error that we commit here is on a functional, so real valued function. Again, under the same stability condition, is up to a constant equivalent to the best approximation error. Then we have error terms that depends on the noise, the random part of the noise, and the deterministic part of the noise. And again, in the estimating expectation, we have this measure of the bad events. That this is a small term, which we don't have in the probability case. So here we are detailing all the contributions. So if we don't have noise, random noise in the measurements, we will have only a bound on the best approximation on the polynomial space, plus, let's say, the best approximation or the discretization error in the physical space. Okay. But again, all this holds if we keep a number of samples sufficiently large so that the approximation is stable. Should hurry up now. So all this was quite general. Now the particularization here is for uniform random variables in -1, 1. And in this case, in an expansion on Legendre polynomials. Okay. Here one of the difficulties that the Legendre infinity norm of the Legendre polynomials is not bounded, but it grows as the square root of the polynomial degree. So this constant here is blowing up when you increase the set. Okay, and here is a result, a bound on this constant here. So we can show that if we work on downward closed sets, no matter what set you pick up in dimension D, and for no matter what dimension, as long as it is downward closed, you can show that this constant is between the cardinality of lambda and the cardinality of lambda square. Okay, so if you want to be sure, you just enforce that M is larger than the cardinality of lambda square, and this gives a stable reconstruction for any downward closed set, any fixed a priori. Okay, so still non-uniform reconstruction. And this we see it numerically when we do uniform random variables and Legendre polynomials. So this is a academic case in dimension 1, so one random variable. We look at the condition number of the Gramian matrix, and if we keep a linear scaling, it does blow up in exponentially in the polynomial degree, and if you keep a quadratic scaling, it stays bounded for any polynomial degree. And if you now approximate a given function, this is a meromorphic function, so you expect exponential convergence by polynomials. If you keep a quadratic scaling, you see the nice exponential convergence with respect to the polynomial degree. And if you keep a linear scaling, if the proportionality constant is large enough, you get the nice exponential convergence. But if you start reducing the constant, at some point, the the rate slightly degenerates, and at some point you lose stability and everything goes up. Okay, so in higher dimensions, things behave more or less the same. So this is an application to this setting here, a diffusion equation with 8 random inclusions. Okay, this is the case with 8 inclusions. This is the case where just we played with 2 inclusions. And things more or less behave the same. You are not able to see this picture, sorry, but me neither, actually. I think the first 2 ones are the error with respect to the total number of sampling points that we use, and we use a linear scaling. So at the beginning, the convergence is quite fast, but because we use the wrong scaling at some point, we lose stability. And if we keep the quadratic scaling, the overall convergence is lower, but nothing strange happens. Okay, well, this was another example where we played with a structure linear elasticity with 7 blocks with some variations in each block, and you have similar results on this time. Okay, last comment on this part. Here, I assume to have a uniform random variable and expansion on Legendre polynomials. If you change the distribution and the corresponding orthonormal polynomials, the relation changes. And for instance, if you use the arc-sine distribution and the Chebyshev polynomials are uniformly bounded. So you can get linear scaling, but with a constant that might blow up in the dimension. Or you can show that you have a superlinear scaling, but with no constant in front. Okay? So if you keep, if you are slightly more conservative and you take a superlinear scaling in the cardinality of the set, you can show that it will work for any, again, downward closed set. Now this is a standard, I mean, well, this is just minimization, L2 minimization. Now, of course, there are the works by Olga wrote on weighted L1, and the question is whether we can import these ideas in this context and get rid of this 2 to the d term here. We have similar results for beta and Jacobi. You get even worse scaling here. You can, and there is this other idea again by Olga on reweighting. This was done for L1 minimization, but applies to the L2 as well. So instead of doing a standard least square, you do a reweighted least square. So you sample from a different distribution. And then here you minimize the misfit, the square misfit, taking the ratio between the original distribution and the corrected one. Actually good idea is to use, if we want to work with a uniform distribution, you take the arc-sine. So you sample from the arc-sine distribution, and you still expand on Legendre polynomials. The reason is that if you do polynomial interpolation, you actually want to cluster the points toward the end of the interval. This keeps the interpolation or the approximation much more stable. And again, in this case, you can show a linear scaling, but you will have again a constant that might depend exponentially on the dimension unless you start reweighting the coefficients as well. The Gaussian case is still, I would say, quite open in terms of theory. There are some proposals of doing this trick here using actually a compactly supported distribution. Seems to be a good idea, but then you have to define correctly the scaling of this. This was proposed in this recent paper. So there is still work here to be done. Okay, how many minutes I have? Almost 0. Oh, okay. Okay, so all what I presented here is in the case you fix the polynomial space a priori, so somehow you have a good knowledge of a sequence of index sets and polynomial spaces. And just to tell you, for this type of problems, this one or this one, actually we can show, well, we know that good choices of polynomial spaces are just the reason being that basically the function here is analytic with respect to each one of those random variables, and somehow is analytic in a tensor product polydisk or polyellipse. So the total degree polynomial space is a good choice. And here as well. Things become more less obvious, let's say, if you play with random fields, because then it's clear that not all the parameters in the series have the same importance, so you have to use some weighted or anisotropic spaces and try to balance. But again, we have worked quite a bit on a way of tuning these polynomial spaces, so we can come up with some a priori choices. But then, of course, we started thinking at what if we want to discover this optimal based on the samples themselves. So not relying on too much on a priori information. And I mean the type of algorithm that we are looking at are greedy type algorithms, where you start you try to build constructively the set one piece at a time. So you start with a small set, and then you look for at the neighbors, and you start including and let this set increase until you reach the maximum stability limit based on the observations that you have collected. So this would be just a very simple example of an adaptive algorithm where red is the set that you have already constructed, and you look for at the neighbors. Either you compute the coefficients on the neighbors, on the green points, or you just project the residual. So that would be an OMP type algorithm, but is on OMP restricted only on looking at the neighboring terms and then picking up the most important ones among the neighbors, and then you update the set and the neighbors, and you let it grow. Okay, so there are two nice notions of margin and reduced margin of a set. So if red is the current set, the margin are all the neighbors, so all the points that can be reached with one move from a current index. The problem of working with the margin is that if you select a certain one or a few terms in the margin, and then you update the set might lose this downward closeness structure. So you can define a reduced margin where you say that the neighbors are only those ones that can be reached by if you subtract one in any direction, you should fall back in the set. Okay. And then if you work with this and you check the largest contribution in the set, and you include in the set and you let it grow, you will have a sequence of downward closed sets. So we started looking at this. Actually, Giovanni Migliorati did some simulations on the sequence of this adaptive algorithm. They seem to work quite well. But in terms of analyzing the convergence of this algorithm, is not easy at all. Actually, well, first you should make sure that if you had infinite measurements, so if you worked with a true L2 norm, the algorithm converges, which is not obvious because you can always find functions for which all the neighbors are 0 and the function is not, and the error is not 0. So your algorithm stops because it misses some pieces. So you have to do something more clever in this direction. And second, even if you have that the algorithm with the true L2 norm converges, it's not obvious that when you use this discrete projection, it will converge as well. So we did one step back and we asked a more fundamental question. So if I was able to compute actually, so as I said, this is a theoretical argument for the moment. So if I have a set lambda, I know how to compute the projection. Now, suppose I were able to do a search on all possible downward closed sets, okay, and pick up the best among all of them. So I call MSD is the set of all downward closed sets of a given cardinality in dimension D. And the point is that this set is always finite because of this downward closed structure, so it has to be connected, okay? So even if in principle I'm not limiting the polynomial degree, okay? So the polynomial degree in principle could be arbitrarily large, but in practice no, because the worst case that can happen is that I put all my multi-indices in just one variable, and since the cardinality is S, I at most go up to degree S, or S minus 1 actually. Okay, so the fact of working with downward closed sets, as a matter of fact, already limits the maximum polynomial degree that we use. Okay, so now the question is, if we were able to compute this optimum here, how would this compare with the best approximation on downward closed set? Okay, and that's getting closer and closer to let's see, L0 minimization is done on downward closed sets. Now this is a nice fact. If you take the union of all downward closed sets, actually is what is called hyperbolic cross. So you can show that this the union has this shape where actually you are putting a constraint that the product of the polynomial degrees of each monomial in the set is bounded by S, smaller or equal to S. So actually, when we restrict the search to this set here, we are sure that we will pick up any downward closed set of cardinality S within this set. So this is, as a matter of fact, our truncation of the universe. Okay. So we can apply the previous results directly by requiring that M should be larger than this constant kappa calculated for this union of sets. The problem is that here we get a exponential dependence on the dimension if we do this. Okay. Yes. Yes. Then okay. Thank you. Here is another estimate. Here we estimated the number of downward closed set in this family M. Okay, I skipped the argument, but we can get this estimate here, and d to the s minus 1 times s minus 1 factorial. And then with this, we used just a union bound on the previous non-uniform estimate. And we can show that we can have a stable reconstruction on any polynomial in P lambda, where lambda is any downward closed set in this family. And what we lose here is that M should be larger than S squared. So the blue part is basically what I had previously, and this extra term. So with this, we have a scaling that is S cube, sorry, times log ds. So it looks bad compared to a compressed to L1 minimization. But the advantage here is that we do not care of a priori truncation of the universe. So there is not a log n universe. So, and having this uniform stability, now we can recover basically the same type of estimates as before. So there is still a dependence on the dimension, and now we're looking at how to get rid of this by using this new other idea of anchored set if you want to work in infinite dimensions. So we say that the set is anchored if the random variables are somehow activated one at a time. So we cannot put polynomials degree of degree larger than 0 in the 10th variable if we have not already activated the previous 9. So somehow we rely on a natural ordering of the parameters. And again, here we use the union bounds. And if we were able to compute the best approximation among all those sets, which is still not practical because we don't have an algorithm that realizes this minimum or is close to this minimum, then under, again, the condition M proportional to S cube log S, we could get optimal reconstruction. So to come into the conclusions, what we have looked at is just in the first part it was just least square minimization on a given set, and we showed that basically, for instance, for uniform points and Legendre polynomials, we should keep quadratic scaling. And in the second part, we look at this more theoretical question on finding also the optimal monotone set or anchored set. So, of course, a natural question is how those estimates would compare with an L1 type minimization as Auger has done, where you instead define a universe, and then within that universe you look for a sparse solution in this set. So, some questions. Thank you for your attention. Sorry?
So you really have an order on these terms. Does this allow you to go beyond, let's say, weighted totally free polynomials? So
yes.
Lambda, which is a hyperbolic clause, that is not.
Sorry. Here. S is, so you're referring to this or to the anchor?
No, the question would be how severe this restriction to this anchored sets really is.
With respect to it's just that, I mean, is a similar set, but it's just that you force, so if I don't put that the restriction, if I am in dimension D, I could expand my set in all possible D dimensions. So I don't know which one is important, so I can look everywhere. If I enforce the ordering, this would mean that in the first variable, I can go up to a degree S. In the second variable, I can go up only to 1 because I activated the first one. In the third one, I can go up to S minus 2 degree. And then I cannot go beyond the S variable because I have to have activated all of them in sequence. So I have a budget S. I have to spend 1 to activate the first, 1 to activate the second, 1 to activate the third, and then I can activate only at most the first S. So it introduces a natural truncation up to S. This. So if I have a budget S, I can at most activate the first S. If I have budget 2S, I can at most activate the first 2S. This is the intuition of this anchored set. So yes, it gives, it has an influence. If you pick up the wrong ordering, of course, you will get a bad approximation. So. Sorry, Chebyshev polynomials and Chebyshev and arcsine or Chebyshev measure. This, well, with the standard L2 norm, I mean those are bounded, but with norm not equal to 1. Where was it? Sorry. So you have that. It does scale linearly, but you might have a growth in this constant. So you can either absorb this constant that depends exponentially on the dimension. Is actually, this is conservative. Well, no. If you bound like this, it will have an exponential dependence. You can either absorb it by taking a larger exponent here. I mean, this is what we look at. So we avoided this exponential constant here by increasing the exponent here. Now, the question is how would this relate if you do a reweighting strategy? This I don't know.
So our bounds are, I mean, actually you get sort of weighted LP bounds on these coefficients, at least for certain points of PDEs, and then it turns out that if you look at this, it's, well, less and less likely that you tensorize like many of the polynomials. So most indices have like
A constant is, yeah.
few of them, a few of the parameters actually active, and then
Yeah.
not 2 to the b, but 2 to the number negative.
That's correct, and this is precisely the argument that is used here to get this other scaling.
Question and a comment. So first of all, do you have any idea whether log 3 over log 2 is sharp? Is that the optimal rate? So we know for, say, stronger polynomials with something in the uniform measure that the cardinality of lambda squared is sharp. So that's known to be sharp, but is log 3 over log 2 sharp?
Sharp as a bound for this kappa, or sharp in
sharp
the...
as a bound for kappa, but is it sharp for the sampling rate?
Sharp, yes, there are sets that achieve this bound. It's just a tensor set.
But is it sharp for the sampling rate? Because this kappa
This I can say.